Okay, everybody. So last time, let's make a brief overview of what we did about the cameras and camera geometry. If I can find where we left. Okay. So at the end, we came to a conclusion, something like this. We said that, okay, given a real world coordinate point x, y, z, convert it to a homogeneous coordinate system, put a 1 in there, multiply it with a 4 by 3, okay, 4 columns and 3 rows matrix, and you get a homogeneous coordinate of the two-dimensional coordinate in the image plane. So what kind of things we have inside this 4 by 3 matrix? These are, first I have, okay, this matrix can be composed of, can be viewed as composition of a translation vector, okay. This is a translation vector that tells us where our camera is in the real world in terms of a translation vector, how much I am shifted from the origin of the real world, and what is my rotation with respect to the real world. Remember, this is a 3 by 3 matrix. Well, this is not identity. Identity is this one. So this is not correct. So this is a rotation matrix. This is a 3 by 3 orthogonal matrix. Remember, the orthogonal matrices are like these, right? If I multiply the transpose of it with itself, I get the identity. That means that the transpose is the inverse of it. Then this is our projection matrix. Remember, this matrix is responsible for doing the projection from 3 dimensions to 2 dimensions. Then we have our intrinsic parameters, okay? So in this case, f is the focal length of the lens, sx and sy are the width and the height of each pixel in my camera. xc and yc is called the principal point. That is the center of my image, okay? So the coordinate of the center of my image. If I multiply them together, I get a, again, as I said before, 1, 2, 3 rows and 4 columns. Let me make this like a matrix like this, okay? So there's a 12 number matrix, and multiply each number, so I get the image coordinate of the corresponding point on my image. So that's what we did. I think we spent like 2 hours to derive all these, and these are called our camera parameters. How many parameters we have? We have 3 here, okay. We have 9 here, and we have 1, 2, 3, 4, and 5 there. Okay, 3 plus 9. Okay, it is 12, and 5 here, total of 17. If you don't consider the other parameters that we looked at, what are the other parameters? Other parameters are the skew angle. Remember, our image plane doesn't have to be perfectly 90 degrees. Just a 0.01 degree difference from this 90 degree will make difference. That's why sometimes we take this number into account too. That's called the skew angle, and it is theta. That's one thing. The other thing is that the distortion parameters, okay? To take the distortion into account, distortion is, remember this one. If there is no distortion from the lens, I would say this, but this is really seen because usually we produce distortion for our images. pincushion or barrel distortion. Distortion happens more when you get away from the center. At the center things are nice, but if you get away from the center, like that, radially distortion increases. Okay, so we modeled our distortion based on this observation, and we said that, okay, if r is my distance from the center, multiply that r with two numbers, okay, square of r and the fourth power of r with two numbers, and that will give you your new coordinate position for x and for y. Okay, so this is the radial distortion parameters. These work very nice, and we find them, and these two will make two more parameters. And these are these intrinsic parameters or extrinsic parameters? Distortion. Are these intrinsic or extrinsic?
Intrinsic.
They are intrinsic. Why? Because they don't depend on where my camera is on the real world, in the real world, right? Extrinsic parameters are your translation vector and rotation vector. They tell you where your camera is in the real world. Intrinsic parameters are the parameters that work with what's going on inside your camera. So this lens distortion, okay, your pixel size, okay, your lens distortion, your pixel size, your focal length, center of image, these are all related to the camera. It changes from camera to camera. That's why they are intrinsic. Okay, so there are two types of camera parameters. One is extrinsic, which is the translation vector and the rotation vector, and all the rest are intrinsic, including the distortion parameters. Okay, extrinsic and intrinsic parameters. Good. Did I miss anything? We looked at this projection matrix, and I think I showed you this one. Okay, this function project points. It says that, okay, give me your three-dimensional points in terms of an input array. You say that, okay, I'm going to give you this. My first point is, for example, 10, 20, 20.1, okay, and my second point is 12.1 minus 7.2, 9.2, etc. These are my three-dimensional points. I give them as object points. Then I will give you my rotation vector, translation vector, and the camera matrix. Camera matrix is the matrix that contains the f value, sx, sy value, and the principal point, those y0 and x0 points. These are the camera matrix. Okay, I give you this one. It is this matrix. I give you this matrix, then distortion coefficients, those 2 or 3 values, and then I will produce you my image points. Okay, so at the end I will tell you that this point, this three-dimensional point in the real world, will correspond to, okay, column number 10 and row number 20. It will give you that. Okay, this one will correspond to column number, let's say, 31 and row number 62 maybe. I'm just making these up. Okay, so that's what this project points function of OpenCV does. You might ask, where are we gonna get this one, etc.? And these all are produced by a process called camera calibration, right? We talked about that last time. So question for you, where do you get your object points? Where do you get the three-dimensional points of the objects in the real world? I like that given these three-dimensional points, I can produce the two-dimensional image coordinates. Okay, this is my real world. In my real world, I have a shape like this, and I have a camera. Camera is looking at this object, right? Or maybe just draw the camera like this, okay? This is my image plane. This is my center of projection. So one ray just hits here, and this point just hits there, etc. So I know that this P1 is small p1 prime, and this p2 will be projected to small p2 prime, right? When this function will transform p2 into this one, p1 into this one. But where do I get this p1 and p2? Well, I mean, nobody knows where the real world origin is. I don't know where the real world origin is. Usually I assume stuff, okay? You will say that, okay? I know this is a cube. I know that this is a cube, and this cube is 10 centimeters by 10 centimeters by 10 centimeters, okay? And I assume that this corner is 0, 0, 0, okay? If this is the corner 0, 0, 0, and if I assume that these are the directions of my axis, then I can find the other positions in the real world and feed them to my project points function, okay? Because nobody defines the origin of this world, right, in terms of 3D geometry. That's up to me most of the time. And well, usually that depends on your camera calibration routine. When you do the camera calibration, you are going to see how we define our origin. Okay?
May I ask you?
Sure.
What if cube moves? What if the cube moves? Is the origin always changing or not?
Well, I mean, that's your problem. I mean, if the cube moves, and if the cube moves, okay, and if you accept your origin as the corner of the cube, of course your coordinate systems are going to move, and your camera is going to move. Your camera is going to move that too, right, with respect to the moving coordinate system. So your rotation vector and the translation vector, they all have to be changed. Okay, if your origin is not with respect to the cube, then doesn't matter where your cube goes, your camera's T vec and R vec will stay the same. But whatever it is, your camera matrix distortion coefficients, they will not change because you're changing your camera position. Okay. Good. Then we talked about the distortion. I think we stopped here last time. We looked at distortion. The camera that we looked at is the standard camera. It just projects three-dimensional word information into two dimensions. And we looked at how it is done. We looked at the parameters of such system. There are other types of cameras that we are going to look at it in a few minutes. For example, one of them is this one. What kind of image is this? Okay, let's look at this one. This is a camera. This is the standard lens. Okay. This lens, okay, this standard lens, camera is here. This is the camera part. Is looking at a surface, a three-dimensional hyperbolic surface like this. This is a mirror, okay? If you look at a mirror like that from underneath, okay, from this direction, if you look at a mirror like that, you are going to see a 360 degree field of view. You are going to see all over your side, all around yourself, okay? So this is really the ceiling. This is really the ceiling. This is the left side and this is the right side, and you are seeing the whole room. Okay, this is not looking at just in one direction. Okay, this is called a hyperbolic camera or the omnivision camera, sometimes omnicam. And there are many ways of doing such a thing. Sometimes there are cameras that can show you all around, including the camera itself. Okay, so panoramic cameras, they are selling those. So this is just one type of camera. Calibrating these kind of cameras are very difficult actually. Okay, good. Another camera is this one. This is really interesting. I think you see examples of this one. Usually they use this in the movies or in things like that. Okay, let's remember our basic. Let's say this is a thin lens camera, and this is an object, right? And this is my image plane. On this image plane, if I am focused right on this object, all the points, all the points that originate from this point will be focused on this part, right? And all the points, all the light rays originate from this point will come to this part. So my object will look like just the other way. It will look like this on this image. I know that. But if I move this object a little bit away from the camera or towards the camera, okay, if I do that, what's going to happen? My image will look blurry, right? My image will look blurry. But how about this? How about this? If I do this, my image plane is not parallel to this lens anymore. My image plane is like this. Okay? So let me continue with this thing. So what do you see now? The upper part of the image, the upper part of the object will be in focus, but the lower part will be blurry, right? Interesting. So I am seeing some part of the object in focus and the other part not in focus. And if I do this in extreme cases like this, okay, I can get images like that. Okay, so some parts are really very weirdly in focus and the other parts are not in focus, and like something like that. Okay, these are called pan and tilt cameras. I can tilt my lens. I can tilt my, see this one? It is tilted. There are screws there and there are screws there. You can tilt your lens side to side or up down, and that will give you those kind of effects. Okay, so it is basically very difficult to get a flower in focus and background in focus altogether, but with these kind of lenses, yeah, you can do that. Okay, so tilt and shift lens. Okay, what else? I'm going to skip this one. Let's look at this one. This is the final one. Did I talk about the line scan cameras? Line scan cameras. Line scan cameras are like this. This is our regular pinhole camera, right? And in the real world, I have objects, and with the pinhole camera, I see an object like this on the image plane. Okay, so basically this is a m by n image, right? So the line scan cameras work like this way. They have only one row of sensors. That's it. Just n, not m, but just n sensors. Okay, like that one. Just a single line of image. Okay, so what you're gonna see is just very small part of this image, this object, right? So why would I use such a thing? Well, this would be very useful for scanners, right? Think about the scanner. What does the scanner do? Okay, it takes thousands of images of the same page, but between each exposure it moves the sensor a little bit. Every time it takes an image, it is 5,000 by 1, okay? 5,000 columns and 1 row, right? So if you keep moving your sensor perpendicular to the sensor direction, so at the end, if you take 2,000 images, your final image is going to be 2,000 by 5,000, very high resolution image of your target. Well, your target obviously should not move, right? Well, for the scanners, that's not a problem, right? For the scanners, that's not a problem because your papers are not moving at all, right? So for the scanners, that's a very good solution. What kind of other environments can you imagine for these kind of scanners or the line scan cameras? Can you give me another example other than the scanners? Very high-tech example, very smart idea. Well, what is the advantage of line scan cameras? Why don't I use a 5,000 by 5,000 camera for the scanner instead of using 5,000 by 5,000? I use a moving 5,000 by 1 camera, right? Why don't I use a regular two-dimensional camera instead of one dimension?
They results with more crisp images since they are
Well, it comes from the camera, right? I mean, I am using a camera to take the picture. If I use a two-dimensional camera, it will be as crisp as the scanner.
But how can I say? You mainly mentioned there are two types of it. One of them barrel and other type of the.
So what? I mean, I am going to get one of those distortions for one of the dimensions
there is,
anyway.
Only one dimension, there will be less distortion.
I never seen a ellipse-like scanned image if the scanner is right. No, that's not it. No. Yes.
Memory constants?
Well, I mean, I have to fit this 5,000 by 5,000 image somewhere, right?
Yes.
So, I mean, it has to come from the scanner. So, scanner has it. So, what is the advantage of having a line scan camera instead of two-dimensional camera? Could it be the cost? Which one do you think is least expensive? One-dimensional camera or two-dimensional camera? One of them has 5,000, okay, light-sensitive transistors. The other one has this many transistors. Which one is expensive? Of course, the two-dimensional is more expensive, okay? And you might say that, well, 5,000 is not a big mark, but there are some extreme cases where instead of having 5,000 photosensitive units, you have 20,000 photosensitive units, okay? So, in fact, you are getting 20,000 by 50,000 image. That's a very high resolution image, and the number of transistors that you're going to use on this one is less than this two-dimensional camera, okay? So, very high resolution that comes at a cost of much less than an average two-dimensional. So, give me the second example other than the scanner for this kind of application. Maybe it is the least expected place. Maybe you might say that, well, I wouldn't think that they would use it in there, but your observation satellites. Satellites are like scanners, right? Satellites that are orbiting the Earth, okay? Let's say this is the Earth, okay? This is my satellite. Satellite is basically a one-dimensional camera, but they move around the world, right? So they scan the world. Every time they get a one-dimensional picture of the target area, and if you stitch them together, you get one big image of the corresponding area. So they work that way too. Okay, so they are basically one-dimensional cameras. One-dimensional cameras. Because I mean they are moving anyway. They cannot stop. Okay, and the Earth is not changing much while they are looking at Earth. Well, you might say that the clouds are coming in and out, but they are doing this in a very, very fast way. So it works very nicely for the satellites. So, and the other thing is this photo finish. Photo finish is, you know, okay, just look at this image and try to understand what's happening. Okay. So it looks like this person is the first one. I think in these kind of races, it is the chest line, right? I mean, the chest crosses the line. So this person is the first one. Jones Marion, time is 21:84. Okay, and the second person is this one. It is this one. Davis Thompson. It is 22:27. And the third person is this one. So it is the chest lines, but they kind of look weird, right?
Yes.
I mean, look at this one. Is this a? I don't think that he or she. I think she, right? Has a leg like that, or I don't think that there is a person like this in this world, right? So what's going on? And why all of a sudden I started talking about this photo finish picture after the line scan cameras? This is a line scan picture actually. So how does it work? They place a line scan camera at the finish line. That line scan camera takes pictures one after the other, but it's very, very fast. It takes maybe 1,000 images per second. Okay? And I know at what second it takes the image. I know that this line here is taken at this instant, 21:84. And just next to it, it is 21:85, 86, and 21:09, and this one is 22:27. So each line, I know its time when it is taken. If you put these lines together, you get a photo finish like that. Okay. So of course this is digitally composed, but before the digital computers and digital cameras, they had this, and they had been using this since 1890 maybe. In 1890, they had exactly the same thing with the film cameras. In that case, okay, it's a line scan camera, but they kept the film rolling. Okay, the film rolls, and the camera continuously takes the images, and they use this photo finish for the horse races actually in 1890s. I am not talking about 1980s. I am talking about 1890s, or maybe 1903 or I don't know, something like that. Okay, so this is photo finish, and it's a different kind of camera. Good. Okay. Any questions so far? So I am done with the introduction to computer vision in our fourth week. Let's start about talking about these images. I am going to do a little bit image processing, not much, but just enough for us to see what's going on with the images. If you took image processing before, that's good for you, but just listen to this. Maybe there are some points that are different from what you know, maybe different node traditions, etc. Okay, so I'm going to talk about filtering, smoothing, removing noise, convolution, derivatives, histograms, and some MATLAB plus OpenCV functions to do those. Okay, so this is the second part of this course. Okay, let's look at this. Usually I'm going to assume that we have intensity images. Okay, we have intensity images. What does that mean? Intensity images are brightness. Each pixel represents a brightness. Well, the ideas are applicable for physical images such as the MRI ultrasound or the depth images, but usually we will assume that we have intensity images. Three types of intensity images we have: either binary or grayscale or color. Okay. Well, for the binary images, everything is either, as the name implies, 1 or 0, binary, black or white. These are the true black-white images, either black and white. This is not a black and white image, this is a grayscale image. Why? Because each pixel, for this one, each pixel value changes from 0 to 255 most of the time. Okay, so it's a grayscale image. So each pixel represents an intensity between very dark to very bright. And this one is a color image. Well, it looks like it is not much color, but as you see, the face of the person is kind of pinkish. The sky is kind of bluish, and the snow is not that white. It is kind of grayish, right? So it's a color image, and each pixel is represented by three values: R value, G value, and B value. So where did we get those RGB values? I mean, who made the decision that we should use these three colors, RGB? Do you remember that?
Because we see in that way.
What?
Because we see in the same way, the RGB.
You mean we as humans, right?
Yes, yes.
Yeah, because it is in the human's eye. The human's eye works that way, so they modeled the color that way. So let's measure the amount of red, green, and blue light amounts for each pixel, and we are going to call it a color image. That's how the human eye works. Okay, so three things: binary images, black and white, very efficient in terms of storage, but representing the intermediate values between black and white is not good. So that's why we have invented the gray level image from 0 to 250. If you have, why is it 250? We are talking about 250, 255, because for each pixel we use 8 bits. Okay, if you use 9 bits, then it's going to be 0 to 512 and etc. Okay, some cameras, they can produce 10 bit images, 10 bit grayscale values, and etc. So I'm not going to look at those. And then I have the color images. Color images are actually, each color image is composed of 3 grayscale images, you may see. Okay, the first grayscale image actually represents the blueness, then the greenness, and the redness. Okay, so red, green, blue channels. So each one is like a grayscale image. So I can take this image, actually this yellow, the green one, and view it as a grayscale image. I can do that. But if you put them together and use special hardware to show it, we observe it as a color image. That's how our brain plus the eye system work. Okay, then another concept of histogram. Histogram is this. Let's say this is a 100 by 100 image. Okay, there are a total of 10,000 pixels in this, right? And I know that each value could be between 0 to 255. Okay, If I make a histogram of this image, what's an histogram? If I count how many zeros are there in this image, and then how many ones, how many twos, and how many threes, and make a graph of like that, this one. So I'm making a histogram of this image. So it looks like in this image, they did not use any of these values after 130 or 40. So I would expect this would be a dark image because it doesn't have any private parts. Well, this histogram doesn't correspond exactly to this image, but if you see a histogram like that, okay, most of the dynamic range of this image is wasted. It is empty. You usually expect more, okay? So it is covered, all of that. So histogram is defined this way, and we are going to use histograms from time to time to understand the images, sometimes to even feed this information to our artificial intelligence routines. Okay, so that's the definition. How frequently each gray level occurs in the image. That's the image histogram. And then we have this issue, we have this problem that we cannot avoid. Images have noise. What's noise? Noise is this. Let's say this part of the room, I take my camera, I took image of the room, okay? Without moving the camera, without changing anything, I took another image, two grayscale images, and I expect them to be exactly the same, but it doesn't happen that way, okay? You will never get the same image of the same scene, okay? You will never get the same image of the same scene, even if nothing changes in the outside world. That's because our electronic components, they carry this noise, okay? If a pixel produces 102 gray level for the first take, without changing anything, it's going to produce 105. There will be a few intensity level difference, okay? So that's the nature of these electronic devices, and we call them noise. Noise, of course, I mean, as the name implies, we don't like it. We try to minimize it, but it is unavoidable, and we have to know how to deal with it, okay? We have to know how to live with it. And noise is random, and it occurs with some probability, and it has a distribution. And as you know from your statistics courses, and if there is a distribution, it is easier to deal with this distribution like a normal distribution, because we like normal distribution. It is well behaved, we know how it works, and most of the time this assumption of distribution works, okay? So we are going to assume lots of either normal distribution or the uniform distribution for the noise, and we are going to indicate in a few minutes, okay? But this is how we model the noise. We say that an image pixel should be perfectly I, x, y. An image I at the position x and y, I should have this perfect pixel value, but somebody adds this noise at that position, and I observe this I hat. Okay, I observe this I hat, and I am after this real IXY. To find that real IXY, I need this one, but I don't know this either. But I have a distribution for that one, Gauss distribution. Maybe using that information I can do something. But you will never get the perfect image pixel for any image. You are going to, you will have to learn how to deal with it. Okay. Sometimes the image noise is like this, additive noise. Well, we can deal with this to some extent. Sometimes it is multiplicative. This one is very bad if those n values are very, very large or small. Okay. And we are going to see the differences, okay? Multiplicative noise. And what did I say? I said that we like to model this noise as a Gaussian, Okay, if you like to remember the Gaussian, see this is a curve of Gaussian. Around 0, it makes the peak. Okay, and depending on the sigma value, this bell-shaped curve, sometimes wide and sometimes very, very narrow. If sigma is small, very, very small, it is very, very narrow. If sigma is large, the bell shape is large. Okay? So you say that to get the I add one value taken from this distribution and add it. It looks like the probability of getting a 0 out of this distribution is the highest. Okay, usually you get something around 0, either +1 or -1 or etc. But the probability of getting a plus infinity or negative infinity is not out of the question. You can get them to, but their probabilities are very, very low. Okay, very, very low. So you get a number from this distribution, okay, proportional to Gaussian distribution. You add it to the original image that we don't know what we are after, and you get your observed image. That's our model assumption of the noise. Okay, model assumption of the noise. Okay, there is one example here. Remember the original image. If that image is modified with Gaussian assumption of noise, you will get something like that. Of course, it doesn't make any sense to add noise to your original image. Nobody wants noise, but just to see what's going on, we can show you these kind of images. Okay, good. It looks like I'm out of time. Are there any questions? If there are no questions, let me take a break. After the break, we will continue. Let's be here around 15:33. 10 minutes.
Hocam ben bir şey soracaktım. Ben toplantıda yaparken hocam bitirme toplantısı orada aldığımı zannediyordum.
He?
Bitirme toplantısı yaparken sizin anlattığınız kısmı hani birazını anlamıştım ama tekrar dinlerim diye düşünüyordum.
He.
Sadece ekranı almışım, sesinizi alamamışım. Bana
Evet.
tekrar anlatma imkanı var. Ben şöyle anladım.
Niye atacağım anlamadım.
Yani MR görüntüleri
Ha,
kullanarak
sen kendi proje konusu.
evet şeyi destekleyeceğiz yani. Aynı kişinin, aynı ekspertin tahminini onun MR
Ders
üzerindeki...
bitsin konuşalım ya.
Tamam.
Bir şey alayım da Cemre bozuluyor. Tamam konuşalım. Söyle.
Ne problem resim yani?
yok. Kaldırdılar. Ya seneye oldukları aynen seneye denk kaldırdılar. Ben de yaz korkuyorum. Yok. Aynen. Bir de ben değil de şimdi daha
Yine filmin oynatıldığı salona bakmak lazım. Ben izlemiştim yani. Star Wars izlemiştim şeyler. Yakup'la falan.
Eski mi hatırlıyorsun? Adı da var yani. Kötü oynatmam orada gerekiyor.
Hocam derse başlamadan önce bir şey sorabilir miyim?
Evet.
Bu ders hibrit olarak görünüyor ya, acaba online olarak katılabiliyor muyuz? Yoksa hani bir zorunluluk var mı? Yüksek lisans öğrencileri için, çalışan arkadaşlar için.
Bunu konuştuk geçen hafta, diğer hafta.
Ha, ben yoktum, kusura bakmayın, tekrar soruyorum.
Videoları izleyin, orada konuştuk. Evet, tabii ki devam zorunluluğu var.
Peki online katılan arkadaşlar için de oradan katılım...
Online katılım diye bir şey yok. Onu derse sığmayız diye düşünmüştük. Ama baktık ki sığıyoruz, online katılım diye bir şey kalmadı. Sadece ders yayınlıyorum ki belki gelemeyenler falan olursa soru sorarlar diye. Online yoklama almıyorum yani. So Gaussian is the model that we are using most of time to model noise, but we like Gaussian for a number of reasons. One of them is this: since it is expressed in terms of exponentials, taking the derivative of Gaussian is another Gaussian, and that's something that we like, and we'll talk about this. So why derivation is important, why are we taking the derivatives, we will see in 10-15 minutes. Okay, Gaussian is not the only distribution that we use. The other one is the normal uniform distribution. In the uniform distribution, I mean, it is not like here, it is the producing a zero has the highest probability in this case. All the rest, I mean, from minus infinity to plus infinity, everything is possible, but producing something around zero is highly likely. With the uniform distribution, you will say that everything from A to B has equal chances of producing. Okay, you cannot, here in this case, you cannot produce a zero, you cannot produce any value larger than B, and all the values between A and B have the equal chance of being sampled. Okay, that's called the uniform distribution. We use this one, but not as much as the Gaussian. Okay, other than the Gaussian or the uniform distribution, a certain type of distribution is the noise is the salt and pepper noise. If this is our original image, okay, salt and pepper noise, it's like salt and pepper really, karabiber tuz. So some pixels are turned to 255, some pixels are turned to 0. So I mean, it is not additive or multiplicative. It is just replacing some of the pixels with the zeros and the whites. Okay, these are salt and pepper noise. It's very different from Gaussian noise or the uniform noise. Obviously, you are losing all the information about the pixels value. Remember, with the Gaussian noise, we had original image plus some noise, right? But this one is not like plus or minus or multiplication. It just replace it, and sometimes this can happen. Sometimes this can happen. Okay, so to deal with the noise, one of the methods that we use is the image filtering. Okay, so we are going to give the definition for image filtering. Okay, and we are going to define it. We are going to give you some formulas. It's not that difficult to understand what image filtering is. The thing is that image filtering is very general topic for image processing, and using image filters to deal with the image noise is just one way of using the filters. Filters are used for many other purposes. For example, for the image noise, denoising is getting rid of the noise, resizing the image, increasing the image contrast, okay, extracting other information such as the edges of the image, detecting some patterns on the image. These are all can be done using image filtering, but for now we are going to look at this denoising an image, okay, making the noise of the image a little bit less pronounced. It's called denoising the image. Okay, before doing that, okay, let's go back and let's try to remember some calculus stuff. Image derivatives and average. Okay, we know what derivative is, türev, right? In Turkish, türev. Image derivative is rate of change. We know that, okay, and basically in physics course they teach us this. Speed is a rate of change of distance. So if you have a function that shows you the distance, if you take the derivative of that function with respect to time, you get the speed, and if you take the derivative of the speed function with respect to time, you get the acceleration. We know this, and there are many ways of taking the derivatives, okay? So this is the basic definition of the derivative of a function. Derivative is basically taking this limit, okay? Very small interval, infinitesimally small, okay, interval. If I subtract that interval from x, and if I evaluate the upper part and divide it by this very small interval, you will get the derivative of that function at position x. Okay, and if this f function is the distance covered by an object with respect to time, take derivative of it with respect to t, you will get speed, and take one more, you would get acceleration. We know all of these, and we are not going to do much about this speed and acceleration, etc. However, we are going to use this a lot for to analyze our images, because what is the derivative actually? The derivative is the rate of change, and let's say this is, let me get one of the images, okay. Let's take this line, okay. Let's take this line, and on this line I have intensity levels, and I'm going to try to, okay, in terms of intensity values and x, it looks like it is getting high and it gets very low, it goes a little bit, then it gets high again, and it is low, and from this point to this point is kind of does that, then it goes high again and gradually increases, and here it goes down. You know what I'm doing, right? And it is way down, then it is kind of does that. So as you see, I mean, I can see this like a function, right? F of x. X is the column number, f is the intensity for that line. If I take the derivative of this function with respect to x, okay, take the derivative of this fx with respect to x, what would you get? It looks like, okay, so this will be my derivative. Here my derivative will be 0, right? Here, because nothing is changing. When I come to here, the derivative is going to be something negative, very large, right? Here, but negative. Then I continue with zeros. Then here it will be large. Then I will continue again with 0. then it will be like that one. Then here is going to be increasing something like that. Interesting stuff is happening with respect to x derivative. And if I take the derivative of these kind of image lines or image columns, I would get valuable information, such as I can find where this head starts, like this, and where it ends, where this column of the background starts, where this part starts, and etc. Right? So derivative is always useful for us in images, dealing with the images. That's why we are going to spend some time taking the derivatives of the images, but images are two-dimensional, not one-dimensional. So we will end up taking derivatives with respect to x dimension and with respect to y dimension. Okay? So we will use this formula a lot. Well, the thing is that this formula is for continuous functions. We don't have any continuous images. Our images are always discrete, so we have to find something that corresponds to this one, corresponds to that one in terms of images. Okay? Everybody knows, remember these. If this is my one-dimensional function is this, if I take the derivative of y with respect to x, this is what you do, yeah? Just 2 times x plus 4 times x cubed. Or for this one, everybody knows that the derivative of sine is cosine, and everybody knows that e to the power something derivative is the same, but I have to take the derivative of the upper part too. So minus e to the minus x. Okay? So these are some derivatives that we know from calculus, but again, our images are not like this. Our images are discrete values in both x and y dimensions. Okay, so the discrete derivatives are taken this way. There are a few ways of it. This is what you do, very crude approximation. For delta x, I use 1. Okay, so I just subtract fx. I just subtract fx minus 1 from fx and divide it by 1, and I call it a derivative with respect to x. So if this is 1 and I ignore it, and this is basically, so basically you just take the difference between two neighboring pixels. That's what we do. Take the difference between two neighboring pixels. And this is as simple as taking a difference between the neighboring pixels. Some people say that, why do you take the difference like this way? How come you are not taking it this way? Well, you can do that. This is called backward difference derivative. This is called forward difference derivative. Some people say that, let's not use the center pixel, let's use the left and right neighbors, so it would be symmetrical. So this is what we do. It doesn't matter which one we use. Usually we prefer this one. So don't get surprised if you see some other way of taking the derivative. So discrete derivative, finite difference methods. There is no other way that we can take the derivative. Could you stop playing with your phone? Okay, thank you. Here are some examples of derivatives with forward differences. I did lots of exercises last year, I guess. Should I keep this? No, I am going to erase them. What? Okay, good. If this is my one-dimensional function, okay, if this is my one-dimensional function, discrete function, if I'm going to take the derivative of it, okay, so obviously here I am taking whatever. Am I doing the forward differentiation or the backward? Which one? Backward or forward? Let's look at this one. So for the first one, it's going to be a problem. Why? Because the first one I don't have fx minus 1. I mean, I don't have this one, right? So for this one, this 0 is not exactly right. Actually, instead of 0, maybe I should have said I don't know, because fx minus fx, I don't know what this fx minus 1 is. I know f0, I don't know what f minus 1 is. So I don't know this one, but this one is very clear. 15 minus 10 is 5. 10 minus 15 is minus 5. 10 minus 10 is 0. 25 10 is 15, and etc. So this is another set of discrete numbers, a new function, and I can take derivative of this one, which is for the x2, and this time 5 minus 0 is 5, minus 5 minus 5 is minus 5, minus 5 is minus 10. This is not correct, right? And 0 minus 5 is 5, etc. Okay, so I use this backward difference operator, and if I use the forward difference, I would do just the opposite. So it is 10 times 15, and except it goes that way, 15 times 10, and etc. So basically what I do is, for the backward difference, I would take this minus 1, 1, multiply this with minus 1, multiply this 1, okay, so, and add them up. Minus 10 plus 15 is 5, and the same thing here too. Minus 1 is here, and 1 here is here. Minus 15 plus 10 is minus 5, etc. It goes that way. So basically I take this window and move it around at each element and multiply it with the corresponding value and add them up. Backward difference for this one, forward difference is this one, and the central difference is this. Okay, so I took the derivative of a one-dimensional discrete function. As you remember, I mentioned this many times. Our images are two-dimensional discrete functions, but if I take a single column or single row of the image, it becomes a one-dimensional function, right? And I can take the one-dimensional derivatives that way. Okay? Okay? So, since my functions are two-dimensional, this is the notation to give you the derivatives with respect to x and y of such a function. Okay, two-dimensional. If I take the derivative of this function with respect to x and y, I would show it with this notation, and usually I would say fx and fy. So at every point I have two derivatives. One derivative with the axis, the other one is for the y-axis. Two numbers. For this one, at each point I have one number, okay, because there is only one dimension. Now since I have two dimensions, for each point I have two derivatives, derivative with respect to x and with respect to y, fx and fy. This is called a gradient vector, and it is shown this way. Okay, don't get confused between this gradient and this delta. This is delta, okay, this is gradient. Okay, gradient of an image is shown like that, and gradient of an image are two images. One output is the x, a gradient with respect to x, the other one is gradient with respect to y, and it is shown this way. Okay, if you like to take the gradient magnitude, you take the square of each component and take the square root, and if you like to calculate the direction of the gradient, you just divide this by this one and take the arctangent of it. It will give you the degree, and we are going to use both of them to do edge detection, and we are going to do it next week. Okay, so to take the derivative of an image, I can do it with like this way or this way, But usually we try to do it in a little bit different way. Usually we do this, okay? To take the derivative with respect to x, I get these 9 numbers. You see these 9 numbers? Okay? Minus 1, minus 1, minus 1, 1, 1, 1, 0. So it is like, this one is like the central difference operator. Okay, but 3 rows. Get these and multiply it with this one. Okay? Add the results up and divide it by 3. Okay, divide it by 3, and that will give you the derivative in the x dimension around this point. Okay, so let's do that. So can you guess what the results would be for this application? Multiply minus 1 with 10, multiply 0 with 10, multiply 1 with 20. So what is it? Minus 10 plus 0 plus 20, it is 10. Okay? And the second one is 10 too, and the third one is 10 again. So I am supposed to divide it, if I add them up, divided by 3 is going to be 10. Okay? The operation here would produce me 10 for this corner, and if I move this window 1 to the right, 1, let me do it to the green, like this, do the same operation, it would produce what? Again, would it produce the same thing? 10? Is that correct? It will produce 10 again. Why? Because this time I am going to multiply this one with this one with this, and that one with that. Okay? It's going to be 10 again. And move. How about this one? How about the last one? It's going to be this window. Since they are all the same numbers and this is symmetrical, it's going to produce a 0, right? So I am taking a derivative of this image with respect to x-axis. These numbers will be 10 and 10 and 0. And if I shift my window a little bit down, and if I do it this way, it's going to be again 10 and 10 and 0. 10, 10, 0, again 10, 10, 0. So I ended up having a matrix like 3 by 3. Well, I used to have a matrix of size 5 by 5. It is now 3 by 3. I lost 2 columns and 2 rows, which I don't like much, but that's what happened. Let's deal with this problem later. Okay, but that's what happened. So I took the derivative of this image with respect to the x-axis. If I do the same thing for the y-axis, what do you guys think I would get? Let me erase all that part. I'm going to apply it on this one. For the first line, for the first application, multiply, and multiply. Zeros I am going to ignore, and here, second one is here, and the third one is there. So it looks like I am going to get what? 0, right? Whatever I do, wherever I move my window for this new, I would get, this is, okay, this is fx and this is fy. Fy would be 0, 0, 0, 0, 0, 0, 0, 0, 0. Is it expected? Why is it happening? Well, it is happening because if I move my window up and down, doesn't change anything. I mean, no changes with respect to y. I keep seeing the same thing, but if I move my window left, right, there are some changes. First, my intensities go up, then it stays flat. But if I move my window up and down, nothing changes. So this derivative stuff is giving me some information about what's going on with the images. And these are useful stuff, and we are going to use them a lot to analyze our images. So that's basically how we are taking the derivatives of the images. And you might say that, who gave you these numbers? I mean, who gave you these matrices? Okay. These are just designed matrices. They designed so that these are good ways of taking the image derivatives, in a more robust way. And these are not only ways of taking the image derivatives, there are maybe a little bit better ways of it, but just simple examples. Okay? And like I did before, this one is giving you some examples. Okay? So, let's see, this one is 10, 10. If I get to the, 10, 10. Okay? So, this guy, we produce only this part. Right? This guy appended zeros all around. Well, it looks like it says that I'm going to keep my original size. For the places where I cannot apply this, I'm going to put these zeros all around. Okay. So I already did that. And for the IY, I get all zeros. So it is IX is this, IY is this. In a way, I had an original image, I get two new images. X derivative image and Y derivative image. Okay? So I produce two images because gradient is telling me that. This operation is called actually convolution. Convolution is, for the convolution you need a kernel. This is my kernel. I get this kernel. I apply this kernel at every possible position in my image, and I produce the results. Okay? So this is IX is the result of original image, okay, convolved by, let's say this is a kernel of Y, KY. KY is a matrix, I is a matrix. If I do the convolution like this, convolution is this. Apply this kernel at every position, multiply and add all of them, and produce me a result. That's called the convolution. Okay? So multiply each number by one, add them up, and convolution is shown this way. Okay, that's the convolution sign. H is the kernel, F is the image itself. It's called the convolution. Okay, and convolution is used a lot. It's a linear operation actually. Since it is linear, I can say it's an associative. Why? Because if you have an image, if you convolve it with I, then convolve the resulting system with F is the same thing as this. Okay, it's a linear operation, as I said before. It is associative, and it has some other nice features too. So we are going to use convolution to apply these kind of kernels to our images. This is a derivative kernel with respect to X. This is a derivative kernel with respect to Y. Convolution is not used just for taking the derivatives. It can be used for many other stuff, many other things. One of them is taking the mean or the average of the images. Okay. Usually we take the average like this, right? I mean, how do you take the average of n numbers? You add them up and you divide it by n. Okay. If you take the weighted mean, you multiply each number with a weight and divide it by n. Okay. But we can use convolution to do those kind of stuff. Back to the Gaussian. Remember the Gaussian function? This one-dimensional Gaussian. Okay, this is a two-dimensional Gaussian. I have two variables now. Remember this? This was the formula. E to the power minus x divided by 2 theta square. Sorry, sigma square. This is sigma, and this is sigma. Okay, with the two dimensions, I have both x square and y square. Okay, and this is a sampled Gaussian discretized. See, at the center I have 1. When I move away from the center, my numbers starts going down. But this is just a sample of the one-dimensional Gaussian. If I have a two-dimensional Gaussian like that, okay, of course it's going to be something like that. At the center, let's say I will have a 1. At the corners, very small values, I am going to put 0, but as I told you before, they will never going to be 0. Very close to 0, but not 0, because Gaussian is defined from minus infinity to plus infinity. Okay, but at the center it is going to be high, and maybe this will be 0.6 here, 0.6 there, 0.6 and 0.6, and it gets smaller and smaller. So it gets smaller radially, so at the center it is very largest, then smaller, then smaller, then smaller. At the corners it is the smallest. Okay, so I can make a kernel like this, a Gaussian kernel, a 5 by 5 kernel, and I can apply that kernel to my images, and that's called Gaussian filtering. Okay, that would be Gaussian filtering, and we are going to see examples of Gaussian filtering in a few minutes. I will come to this later. I will skip this one. Okay. So we talked about the filtering. Anyway, I'm going to skip this one. Okay. So if this is my image, if this is my kernel, well, I cannot do much with this example because I cannot move this kernel on this image anyway, because this is 3 by 3, this is 3 by 3. There is only one position that I can apply this. It is this position. So 1 times 1 plus 0 times 3 plus 0 times minus 1 plus 2 times 1 plus 10 times 0.1. If you add them up, if you do these 9 multiplications and 8 additions, you will get a 5. That will be the filter output. Okay, with the convolution. Well, this is a unique situation because, as I said before, I cannot move this kernel on top of this image on more than one place. There is only one applicable place. Usually we put zeros around it because I cannot calculate them. There are other ways of dealing with this problem too. Okay, this is application of the linear filtering convolution to this image. Let's say this is my 100 by 100 image. 100 by 100 image. And I like to apply this filter 0, 0, 0, 0, 1, 0, 0, 0, 0 to this image. Okay? And start from this corner. Let's say this is my corner. And these are my values. Let's say my values are, I don't know what kind of values are there, but let's say these are 100. 100, 100, 100, 100. You get the idea. This is a constant section of the image. And if I apply this kernel 0, 0, 0, 0, 1, 0, 0, 0, 0, what would you get if I apply this kernel to this corner of the image? you would get 100, right? 100. And in fact, it looks like I am ignoring the rest of the pixels around the center pixel. I get exactly the same thing as the center pixel. Okay. So if this is my filter, I would get exactly the same image. Right?
We lost the first and last rows and columns.
What's that?
We will lost.
Yeah. Well, yeah. For the border pixels, one row above, one row below, at the bottom, one row left, one row right. We are going to lose them. They will be all zero. Other than that, the rest of them will be the same. Okay. So this is a very simple filter. Applied it, we didn't get anything new. Well, not much use for it, but it's good for showing you what's going on. How about this one? What did it do? One is not at the center, but it is on the right. It looks like it shifted everything to the right, right? It is not, the centers are not the same. So I say that, shift everything to the right. I'm going to use a single column on the left. Not much of a useful filter, but it's just a filter. Okay, just a filter. How about this one? How about this one? Everybody is just 1, and I divide it by 9. So 9 is not by coincidence, it is calculated. It is the total of this one. What kind of effect did I get? It is a little bit blurry. Why? Because for every pixel, it is taking the derivative, or it is taking the average of the 9 values, right? This is the, okay, 9 pixels. Take the 9 pixels, add them up, and divide it by 9. So it just takes the average of it, and do the same thing for all the pixels in the image, and this is what you get. Okay, everything is, so I lost lots of detail actually. See the details. There is a kind of a line here, another line there, another line there. What happened to those lines? Yeah, I don't see them as good as before. I kind of assume that there are lines, but they are all gone. So I lost the detail. I don't see the details anymore. Okay? Sometimes losing the details is important. Sometimes I don't want to see the detail. Okay? Sometimes I like to see the general structure of it. Maybe this is a good filter to remove the detail out of an image. Okay? Remove the detail out of an image. Maybe I could, this is definitely more useful, more meaningful than especially this stupid filter, which didn't do anything. This one shifted all the image columns to the right. This one took the average, local average around each pixel. My image is kind of blurry. Remember our noise models, remember the Gaussian noise? This might be a good way of handling that noise, right? Taking the local average of the pixel of the image around every position, then that might be a good thing actually, because I am taking the average around the neighborhood, and if I add all the, remember this nx, if I take this from the Gaussian distribution is symmetric around 0, right? Sometimes it gives you a negative number, sometimes it gives you a positive number, sometimes around 0. Okay, question for you. If this is your Gaussian, if I take 100 samples out of this distribution, 100 samples, and if I add them up, what would I get? What would be the total? 0. Why? Because it is symmetric around 0, right? It is 0. So if I know that this 3 by 3 region is is added noise by this Gaussian distribution. If I add those numbers up, what am I doing? I am cancelling out the noise part. And if I divided that region by 9, so the noise part is cancelled out, but I took the average of nearby pixels. Okay, my image is a little bit blurry, but I took care of the Gaussian distribution results. Okay, maybe I could say that. So if the images is corrupted by the Gaussian noise like that, maybe this kind of filtering is good for me. How about this one? What happened? It's a 5 by 5 filter, right? 5 by 5 filter, and if I convolute this image with this filter, I would get this. This one is even more smoother. Okay, I lost much more information, but the image looks more smooth. Okay, smoother. Okay, so if I make the filter larger, that's what I would get. How about this one? Interesting. So first of all, what kind of filter do you see here? It's not all ones, it's not all zeros, right?
Two-dimensional Gaussian.
It's like this, right? In both in X and Y dimensions. It looks like Gaussian, right? Two-dimensional Gaussian. So if I apply a two-dimensional Gaussian on this image, I would get this. Okay, again, the image is smoother, but it is a little bit better behaving smoothing filter. Okay, we like the Gaussian smoothing better than the averaging filter. This is averaging filter. It takes the average of local regions. This one takes weighted average of local regions. It says that central pixel is the most important. Okay, pay more attention to the center pixel. Okay, pay more attention to the center pixel. And if I get away from the center pixel, their weights are smaller and smaller. When you reach to the outer parts of it, your weights are as small as 0. Okay, we like Gaussian because first thing is it is rotationally symmetric. Okay, if you rotate this one 30 degrees, okay, how about this one? If I rotate this image around the center 30 degrees, what would you get? Or 45 degrees, you would get something like this, right? One's there, one. So effect of this filter with respect to this filter are two different things. But if you are applying a Gaussian, since Gaussian is like concentric rings like that, doesn't matter if you have a rotated image, it should behave the same. At least this part is good for the Gaussian. Now there are other nice properties of Gaussian. Let me go back to that slide that I skipped before. Okay. Properties of Gaussian is the most common nature model. Smooth function, it has infinite number of derivatives because it is e to the power something, right? If you have a e to the power something, x, etc., if you take the derivative of it, this will never go away. Keep taking the derivative of it. That's good. It is symmetric around the center. Okay. And if you go to the frequency domain, which I will not talk much about, it is exactly the same thing Gaussian. And the thing is this, okay? The thing is this. If this is my image, I can take a convolution of this image with a kernel, or I can take a convolution of this image by itself. Okay, it can happen. An image is a two-dimensional matrix, right? Kernel is a two-dimensional matrix. I can do that. Okay. If I take the convolution of Gaussian with the same Gaussian, the result is another Gaussian. Okay. These are very nice features of Gaussian. And Gaussian is separable. That means that you can do the Gaussian you can do the Gaussian filtering by using one-dimensional Gaussians in X and Y dimensions, and results will be exactly the same thing, which will be very, very cheap, cheaper than two-dimensional Gaussian. Okay? So that's why we like the Gaussian a lot, and this is an example of weighted filtering, and maybe it is Gaussian too. So these kind of smoothness functions are much better than averaging filtering. Okay, averaging filter is this: take the average of 25 numbers. This one says that take the average of 25 numbers in a weighted way. Okay, center as the most weight. And how am I going to choose the weights? You choose the weights using the Gaussian distribution. Okay, that's called the Gaussian filtering. Okay, so and these are some of the the same filter size, but one of them is averaging filter, the other one is Gaussian filter. Okay, as you see, some parts are jaggy here, this around the eyes. You don't see that jagginess on this one. Okay, especially with the objects with the corners. Okay, so we prefer Gaussian smoothing most of the time. Okay. Noise filtering, as I said before, if this is an image that is corrupted by Gaussian noise, if you apply the averaging filtering, you would get this result. If you get the Gaussian filtering, you get this result. And we usually prefer this one over this one, as I said before. Okay, so this is the filter that we kept applying all the time. 3x3 averaging filter. I'm going to skip this. Well, I mean, can you guess what kind of results we get? What kind of image is this? It is a 1, 2, 3, 4, 5, 10 by 10 image, right? 10 by 10 image. The surroundings are all 0. In the center there is a bright part, but there is a 0 here, there is a 90 there. If I like to apply this one for this image, what would I get? Of course, the convolution. Let's do the corner first, okay? It is all ones, right? Let's do this corner, this part, this corner part. Can you see the color? Maybe the green is better. Yeah. Okay. If I apply these to this one, it's all 0, so you're going to get a 0. How about this position? What would I get? You would get a 10, right? Why? Because I am only doing, why don't I? Can I do that? Can I? Yeah, maybe move it. Yeah, it works, right? Move it like that. Good. I moved my window and multiplied each value with 1 and divided by 9, I would get a 10. So it looks like it's going to be 10 and 10. No, this is not 10, right? This 10, then it is 180 divided by 9 is 20. Is that 20? Then how about this one? This is 30, maybe. Then this one is 20 and 10, and is that correct? 0? No,
Another 30.
There will be another 30. So how many 30s will be there? Just 2 30s. Then 20, then 10, then 0. Right? How come it is? No, it is not correct. There will be 3 30s? No. 1 30 here. Yeah, there will be 3 30s, that's true. So 30, 20, 10. And I'm not going to put a 0 in there because the meaning of that 0 is different than the meaning of the 0. And if I continue this, I can fill this image up. This part is interesting. See this part? Because of this 0, first of all, the pixel that corresponds to this one will be here, 1, 2, 3, 4. This one will be 90, right? Because for that one, everybody is 90. But for that one, it's going to be a little bit lower than 90. Anyway, let me move and let me show you the final results. We need that before, okay. So this is about nice they did this, right? So the brightest parts are there, then we have 80s. So really it smoothed the image out. We don't see any zeros in there and we don't see it in 90s. Right? In natural images, in regular images, you don't see these kind of crazy pixels, right? I mean, it is very difficult to have a 0 inside a bright region, or it is very difficult to have a bright pixel inside a dark region, okay? So by doing this filtering, I get rid of that problem. And in real images, actually, you don't see these kind of sharp changes from 0 to 90, okay? Maybe in synthetic images, but in natural images, you don't see those kind of changes very often. So filtering, in this case very simple average filtering, can take care of those kind of problems. Okay. So box filter, we talked about it. Okay, there is one example of box filter. So very simple. Okay, this is our kernel. This is our kernel. This kernel is maybe like this. Okay, it is like maybe 5 by 5. Let's say it is 5 by 5. It is all 1 1 1 1 1 1 here and all around zeros. That's why it looks dark around and bright at center. Okay, so if I apply this kernel, 5 by 5 kernel, to this image is blurred, of course. And if I do the same thing, okay, original filter, the same thing. Okay, I did that already. Well, what do you think is going to happen? What kind of crazy image is this? Multiply each pixel by 2 and subtract the local neighborhood average from that one. Take the local neighborhood, right? Take the local neighborhood average and can you imagine what's going on? Let's do this on a one-dimensional image. Or maybe I should take a 15 minutes of break. Let's take a break first, okay? When you come back, we are going to try to figure out what's going on here, okay? 15 minutes break, and after that, just think about this, okay? So we will be around 16:44. Bir de herkes bunu imzaladı mı arkadaşlar? İmzalamayan var mı? Barış Onur, senin ismin niye yok listede ya? Ha?
Benim var hocam. Benim.
Barış.
Başka Barış. Hocam dersi
Barış
ilk bıraktı. Aldım da ben.
Sen kayıtlısın ama değil mi?
Evet hocam kayıtlıyım.
Ha, tamam, güzel. Ben bunu 2 hafta önce almıştım.
2 hafta kaydoldu değil mi hocam?
Ne oldu?
şeye girdik geçen aylarda işte Mart'ta havalar sıcak olur. Mart'ta Ramazan başlamadan Haziran başlıyor başlayacak. Galatasaray'da çalışmaya geldik.
Rüzgar yapıyor mu?
Var da.
Geçen hafta yaptı.
Sen yapıyor musun?
O hangi ara gittin?
Bizden zaten Ramazan başlıyor. Neyse Mayıs'ta başladı burada sizde.
Başkanı nasıl yapıyor mühendis onu? O ünlü ama nasıl mühendis mi?
Üniversite mi?
Robotik kulübün başkanı.
Benim de.
Robotik kulübü var.
Robotik
Kardeşim antreprenörün başkanı bilgisayar mühendisi olur. Robotik başkanı şey makine olur. Elektronikçiler o kafasını iki yapıyor. Podcast dersinin için bir tane robotik kulübü başkanı. 4. yılda robotik kulübü başkanı. Kolay gideceğiz ama benim bildiğim şeyler alın çıksın. Uğraşma. Ama pislik yapmaya şey yapmış olurum. Şey evinin yanında orada yapmışsın. Gel birkaç lira götür ara da kanka. Bekleme ya bu soruyu. Bekletelim. Bence gerekirse eve gitmek istiyorsan eve de götürsün reis. İlla havama gideceğim diye düşünme yani. Bana sorabilirsin adam Atışehir'de oturur. Belki de bir eve götürsün. Sen şey biliyor musun? Bu Mahmut geldi ya, büyük kafamda. Bir gün geldi mi? Dedi ki, Stepol Flores hava açacaksın. Hava Stepol. Açacak mısın? Bilmiyorum. Onun hocası sordu. Dedim ne oldu ki? Ben açtım, soruyu yayınlayamadım, sen yapacak mısın? Kafayı nasıl öldüm abi? O sırada çok gördüm. Dedim şu an işim yok, daha sonra baksak olur dedi gitti. Bak şakasız değil.
Şöyle basit şeyler izledim ya ben. Çok iyi şeyler.
Nasıl? Nasıl sorun? Çok tilt oluyorum. Çok sinsi kanka.
Ama o hafta verdi. Sinsi. Değil mi?
Bence sinsi. Diyor ki, sözleşme aldım. Nerede beni bir yıl sonra imzalı diye şirketleri. Tamam kardeşim, bana da iyi yapmışsın, ne bileyim. Adam dese ki senin sözleşmen bitiyor, sen ne yapıyorsun, ne yapıyorsun?
Anladın mı ya söylediğinizi?
Şeye bak, bizden önceki ilk çocuk, şimdi Emre diye bir çocuk vardı, o da ilk çocuk. Yüksekten gitmiş, Sakarya, şey var, mevki, üst sınav,
Lisanslı oldu da yüksek sanatın sadece.
yok yüksek sadece.
Geçensene neyi? Aselsan'da bizim bölümleri, öteki bilgisayar, iş ekmeği, her şeyi de. Aynen bilgisayarın ağzına çıkarmış. Geliyordu. Bak, o kadar ilginçti ki saat 7.30 mesai başlıyor orada. 7.30'da geliyordu. 9'a kadar uyuyordu kapıyı. Vallahi bak yemin ediyorum Allah sırtını çeker. 9'a kadar uyuyordu. Sonra ben kalkıyor gözler şey. Dedi ki ben 7.30'da geliyordu. Söyledi. Yani öğlen kadar oturuyordu. Öğlen yemeği sohbet ediyordu. Ondan sonra dedi ki ben çaycıyım gözleri kapalı. Çekiyordu. Ama sonra şey oluyor. Bunların bir kişi ayrılmışsa sonra benimki içmeni şunu yapmak lazım. Benimki içmeni ayrılmadan böyle ayrılmışsa ben şunu yapıyorum. Bir zaman çıkartmak için
Kopu yok. Evet, oturuyor.
Ya da bir nokta var. Hayır, ben tabii.
Doğru.
Ben de bir kullandığım için bilmiyorum.
Şu an
Peki, çalar mısın? Bunu alır mısın?
ben bilgisayar başlıyor.
He?
Bilgisayar başlıyor. Ne kadar ki?
Bilmiyorum. Yani bir çalar mı?
Okay. So what is this? Can you guess what this is?
It enhances the edges, makes the image more sharp
So how did you know that?
from the image processing course.
From the image processing program. Okay. So it's called sharpening filter. It enhances the edges, but how does it do that? Let's look at this one. Let's say I have a function like this, and function does such a thing. Okay. If I take the derivative of this this function, this would be the derivative, right? For this part, the derivative would be all zeros, right? But for this part, it will be increasing and coming back and doing this. Okay, that's the derivative. So by multiplying this function with 2 first and removing the average of it from the function itself is going to be, let's take the average of it. The average will be, and this will be the average. Average will be, first of all, it will start around here like that, and it will end around here like that, and it will be smoothly doing this, right? Maybe I didn't do it very good. Let me try to do it again. Okay, so it will start like that, smoothly it will go, and smoothly it will converge. So this part and this part will be the same, but only during the transition, the transition is smooth for this black one, which is the average one. So this one says that subtract the average from the original function itself, but 2 times the function. If I subtract it from the original, let's get rid of this derivative. I don't know why I tried to explain with respect to derivative, but I'm not going to do that. Let's do this part. Let's subtract this black from the blue one. I am going to get this if I draw it with the red, like that, and like this, like that. Okay, around 0. If I do the subtraction of this red out of the original one, this will be the final result. It will be like this, and like that, and like this. So what's going on is, around the shifting positions, around the positions where the edges are happening, I am putting a more difference between the left side and the right side. Okay, so the human eye, for some reason, sees these kind of edges transitions in a better way, favors it, and we like it better. We think that the image is sharp. Okay, that's why they call this the sharpening filter. Okay, so if I apply it to this one, we think that it looks sharper. Of course, since this is pixelized, doesn't look that nice, but as you see, the contrast around the center part of the eye is much higher for this one. And if I look at this image from a distance, for our eyes, maybe I should do this. Do you see the difference? No? That's too small. How what? Yeah, maybe like that. Anyway, I mean, they did the experiments and humans like this one much better. Okay? It contains the same kind of information, but people like these kind of images better if the sharpening is applied at the right amount. If you do this too much, then people don't like it much. So there is a trade-off. Okay, good. So this is a smoothing filter using the Gaussian. Remember this one? This one was the smoothing filter. This one was the smoothing filter with the box filter, just that square kind of filter. The result with the Gaussian looks much better. You don't have the jaggy edges. Everything is smooth. Okay, and this is the box filter. This is the Gaussian filter. We prefer the Gaussian for many reasons. Okay, and again, as I said before, image filtering convolutions are very useful. They are not just used for taking the noise out. They are used for, such as the sharpening filter. Okay, they are used for taking the derivatives. They are used for many other purposes. And the nice thing is that they are linear. Okay, convolutions are linear. What is linearity? Okay, if my filter is linear, then it can do this. Doesn't matter if I add those two functions and apply the filter, or apply the filter then add them up. Okay, or I can do this: shift the image left, right, up, down, apply the filter, or apply the filter and shift left, up, down. Doesn't matter. Shift invariance is a property of linearity, and we like those. And other stuff like this commutative, doesn't matter you do this or that. Okay, it's like plus or multiplication. Associativity is there too. Distribution over addition is always there. We already did that, right? And the scalar factor out doesn't matter if you do this Ka convolved with B or A times Kb, it's the same thing. So many useful stuff with the linear filters. Okay, linear filtering is something good, but there are other types of filters, such as the median filter, that is very useful, but it cannot be implemented linearly. I think this is the best example of non-linear filters, median filter. Median filter is this. Remember what we do? Okay, if these are original image, and these are kernel, we apply this kernel to this corner and move the window around like that, right? And this is the convolution. This is linear filtering. With the median filtering, this is what you do. You get to this window. Okay, let's say this is a 3 by 3 window. You sort all the elements inside this window and take the median of the window. Okay. Of course, to take the median, you need to sort the elements and take the median value. Remember, median is just the center value of the sorted pixels. So you do lots of sorting for each window and take the center one. Sort and take the center one. That's what happens with the median filter. So it looks like, well, why are we doing this? Well, it's going to be very useful for some cases. For example, remember salt and pepper noise? You replace some of the pixels with black ones and some of them with the white ones, right? That's what it is. So if I apply a Gaussian filter to this salt and pepper noise, this is what I get. For the mean, this is what I get. If I apply the median, this is what I would get. So median is behaving much better. Why? Because you would think that in a 3 by 3 window, one, maybe 2 pixels are affected. Okay, 1 or 2 maybe they are turned into white and black maybe. The rest of them are okay. So if you take the median of such a window you will say that that's the original pixel without getting affected from the salt and pepper noise. That's why we like median filters for these kind of cases. But if your noise type is Gaussian noise, then the Gaussian convolution, Gaussian filtering is a much better solution than the median filter. And as I said before, median filter is not a linear filter. It cannot be implemented using the convolutions. It doesn't have this associativity and other kind of nice features. You cannot cascade them, but if it is useful, why not use it? By the way, if you apply a very large filter to this image, it gets blurry and you start losing the edges. With the median filter, you don't lose the edges. Edges are okay. See the edges here? I can trace this line here and this line here. I didn't lose that information, but this one starts losing these kind of edges. Okay? Median filter doesn't lose them because it just picks the median. Okay, one question here is that we talk about 3x3 filters, 5x5 filters, 7x7 filters. By the way, why are we using the filters in odd sizes, not the even sizes? We don't talk about 2x2 filters, right? Or 6x6 filters. We think about them like 3x3, 5x5, 7x7. Why do you think that? Yeah?
Because I think we need a center point.
We need what?
A center point.
Yeah. Well, I mean, with the 3x3 there is a center pixel, right? That filter is symmetric around that center pixel. That makes lots of processing a lot easier. I mean, corresponding pixel finding it. That doesn't mean that even size filters are not possible. It is possible, but usually we prefer odd size filters. Okay. So let's look at this problem of what happens around the borders. One thing that we did was the clip around the border. Okay, so put zeros around it. Don't make your image smaller. Just put zeros around your image where your filter is not working right. That's one thing. Clip filter. Okay. The other one is wrap around. Okay. Wrap around is this. Did you understand what wrap around is? So at this position first, enlarge your image a little bit. So take some part of your image like this and put it there, and take this part and put it here, and from left to right and from right to left, right? So this is called wrap around. So you made your image a little bit larger, and now you apply your filter, you will get this. This would be your final result. Okay? This is called wrap around. Okay? And then we have another kind of heuristic solution. Another kind of heuristic solution is copy the edge. See? Make your image larger by copying the first column, last column, the last row, and the first row first. Okay? Make your image larger a little bit and apply your filter, and this would be the result. Okay? And the final one is the reflection or the mirroring. This is what you do with the last one. Okay? Did you understand what's going on? Let's look at this part. This is the original border. So I am just copying this part to this part, right? But in a symmetric way. So like this. And the same thing around here, like that. Okay? So this is called reflect across edges, and if I apply my filter after that, I would get such a result. So these kind of things are usually available for you to to choose from your library, whatever library you are using. In MATLAB, I mean, whenever I forgot where I have stolen these slides, but of course we don't ask you to use MATLAB. Instead, we have our OpenCV, and if I let me go to this, okay, OpenCV image filtering. We have a number of nice functions in OpenCV to do this kind of stuff. I'm going to skip this. For example, this blur, function blur, okay, it takes your input image, it takes your output image, and it is a kernel size, what kind of size I am going to do. And for the border, what am I going to do? I mean, am I going to do this zero padding, or the reflection, or the wraparound, and etc.? And this will blur your image. So this will not take a kernel, because it is going to use the Gaussian filter. No, normalized box filtering, sorry. Normalized box filtering. And if you like to use other type, for example, for the general one, filter 2D, okay? It takes the input and output, and it takes your kernel, okay? Where is my kernel? And this is your kernel. You can provide any type of kernel, including the Gaussian, or any other kernel that you like to try, and it's going to give you that one. If you like to do the Gaussian directly, again, with the sigma value and that kind of stuff. So we have all kinds of possible filtering techniques, including the median, okay? So this, for the median, the only parameter is the window size, 3 by 3 or 7 by 7, whatever. Okay? And this border default, let's go to the borders. What kind of border values we have? Okay. Where is it? Okay, borders. Yeah. So constant borders, you can specify. Okay, this is good, right? So you append these eyes, whatever they are, specify the eye. If it is 0, then it becomes the clipping. Replicate is just do the copying of the first and last, right? Reflect is this. Wraparound is this. Border reflect is, what is this? Oh, okay, so it starts from, not from A, but starts from B. Border transparent, I don't know what is border transparent. I don't know, I mean, can you guys think what this is? Okay. Border transparent. Put some unrelated stuff. I don't know. I don't know what this border transparent is. Just read the description. Okay? So, but we have these kind of filtering help from the OpenCV. I guess that will be it for this part of the lectures. Okay? So basically, I told you about the convolution, and I told you about the Gaussian filtering. I told you about the Gaussian noise. By the way, Gaussian noise and Gaussian filtering are two different things. Okay? The fact that we are applying Gaussian filtering, get rid of the noise, is not because of the Gaussian noise. Okay? I mean, they are just models. I mean, we use Gaussian for many things, and in this case, it happens to be that we use the Gaussian to model the noise. Also, we use the Gaussian to produce our kernels. I mean, they are not because the name Gaussian is common. The name Gaussian is common because of just coincidence. Okay? So I talk about Gaussian filtering, median filtering, convolutions. We are going to use convolutions a lot. Convolution is an expensive procedure actually. Let me go to the convolution slide, and if I okay, where is my main convolution? Yeah, there it is, the convolution. So for every pixel of the new image, KL, okay, I need to do this multiplication and addition. So for every pixel, that means that if my new image size is k, let's say m by m, so m square comes from there, m square times size of my filter. So it is quadratic with respect to the size of the one size of your image. So it is expensive. So it makes sense to find a nice implementation for your filters. OpenCV implements it nicely. Sometimes you can get, instead of n square, order of n square, n is the size of the stuff again. We can get n log n complexity numbers if you go to the frequency space. Frequency transformation is something that, as I said, I am not going to talk much about. But if you go to the frequency space, things are a little bit cheaper. But it has some other costs. For example, in the frequency space, some kernels doesn't behave the way we want, but the Gaussian behaves exactly the way we want. That's why we like the Gaussian, because the Gaussian, the frequency domain representation of Gaussian is the Gaussian itself. That's why we like it there too. So it is both fast and nicely behaving. Good. Any questions? If there are no questions, let me start the topic number 3, which is the edge detection. Okay. Using all these things that we have learned, okay, we are going to talk about edge detection. I have stolen these slides from Mubarak Shah and Alper Yilmaz, and they have taken lots of input from other people and kind of blended in some other slides. So at the end I forgot where I got them most of the time, but they are not mine. Okay, so we are going to talk about this gradient image edge detection. For that one, we are going to use lots of operators, especially taking the derivative of the images. Okay, so our goal is edge detection. Okay, so identify sudden changes in an image. That's the definition of the edge for us. Identify sudden changes in an image. Okay, that's what we are going to call edges. You might say that, well, edges for me is the borders of the objects. I mean, sudden changes don't mean that they are edges. Yeah, that's true, but that's our definition of the edges. For example, there is an edge here, but this one doesn't correspond to an object border, right? But it corresponds to a sudden change in the image intensity. You might say that, right? So it's going to change from image position to image position, and our edges that we are going to recover, they don't have to correspond to the real object edges, but this is what we can do at the beginning, because we have to define something for us. So intuitively, most semantic and shape information from the image can be encoded in the edges, but they don't have to exactly correspond to the shape information of the objects. This is an image of a bottle. If I extract the edges of this image, I get this. Okay, so this is a binary image, ones and zeros. It looks like zeros are the edges, ones are the no edge positions. It looks like for these edges, okay, it corresponds to the object border, but how about this one? There is an edge here and there and there and there. They don't correspond to the object borders at all. And on the bottle itself, let's look at this one. See this one? This one shouldn't have an edge, because it's just part of the bottle because of the reflectance from somewhere else. I don't know where it is coming from. we see an edge. So, well, you might say that the pixels that I marked with edge label doesn't correspond to the the object borders. Yeah, that's true, but that's not our definition. Our definition of the edge is this: sudden changes in an image. Okay, sudden changes of intensity in an image, and it looks like, yeah, there is a sudden change of intensity here, and there is a sudden change of intensity there. We like these positions because the sudden change of intensity corresponds to bottle corners, bottle edges, but this one, no, it is not, and there are many other places. So it is better than doing nothing, but that's the idea. The similar thing is here. Okay, if I extract the edges of this nice picture using some kind of an algorithm, this is what I would get. But our object borders are very different than what I am getting from this edge detection, right? So let's make this clear at the beginning of this edge detection. Edge detection doesn't, its purpose is not to give you the edges of objects. Its purpose is to give you the sudden changes in the image intensity. That's what we are going to do. And sudden change in the image intensity means that take the derivative with respect to x and y. Okay, derivative is very good to detect those kind of stuff, and that's what we are going to do in this chapter. Okay, so this is another example of edges, as you see. So most of the edges, they correspond to the objects, people, their facial structure, etc. But some of them are not there at all. Okay. Maybe I shouldn't talk about this. Maybe this is a better image to talk about, right? So edges happen, I mean the sudden changes in image intensity happens because of these kind of situations. Okay, first of all the depth discontinuity. What does that mean? I mean, there is background of the image, there is a foreground. The background and the foreground image intensities are usually different. Okay, this depth, this continuity is usually the object borders. They are the object borders. So there are edges around this object like that. Okay, they are mostly depth discontinuity related stuff. These are the stuff that usually correspond to the object borders. But there are other type of edges too. For example, there is an illumination discontinuity. This is the shadow of the bottle, right? Shadow of the bottle. It is on the table, but there is a very nice edge around here, because around here there is a sudden change of intensity. Okay, inside this region it is all dark. Okay, outside of that region it is not that dark, it is bright. So there is an intensity change in there. This is caused because of the illumination discontinuity, and our edge detection algorithms are going to find it. What else? Yeah, well, I mean, definitely I am going to find an edge around these letters. Okay, these edges, they don't correspond to objects, they don't correspond to illumination changes, but they correspond to object surface feature differences. Okay, on my object surface, these writings there are, right? And I'm going to produce these edges, and these edges, they don't correspond to the objects. Sometimes I get these kind of edges too. Sometimes I get these kind of edges. It is because of the difference of, or the same thing is here, right? The surface normal is up at the top, and surface normal is towards us, right here. So the surface normal discontinuity will create edges. So the whole idea of this figure is that whatever edge you are finding, we call it an edge because it's a sudden change in the image intensity. It is not because it corresponds to the object borders. Okay. When you don't think about it this way. Once I find the object, once I find the image edges, that means that I am locating my objects or anything like. No, it won't happen, because there will be many other things that will correspond to the edges in the images that are different from the object borders. Okay, so keep this in mind when we do the edge detection. Okay, we will fix that one, and maybe I should stop at this point because we are out of time. Next week I will start from this position, and I will hope to finish edge detection next week. Okay, any questions? Okay, then that's it. I will see you next week.